Hello and welcome back to this video series about the Intermediate Math League of Eastern Massachusetts. Today we're going to be starting up the number theory section for Meet 2. So let's get right into it. Now before I get to the first topic, I would like to let you know that throughout this lesson I'll be assuming that you already have a basic understanding on number theory Meet 1. The material from number theory Meet 1 that you specifically need to know about includes prime numbers, natural numbers, whole numbers, composite numbers, integers, and exponential notation. Now, if you're not familiar with any of those concepts, I would recommend watching my first number theory video on Meet 1, where I'll be able to explain all those concepts. However, if you're familiar with those concepts, you can just completely disregard what I just said and continue watching. So first we'll be starting with the fundamental theorem of arithmetic. The fundamental theorem of arithmetic is a theorem that states that any natural number greater than 1 can be written as the product of only prime numbers. So here I have examples. So 4 equals 2 times 2, 33 equals 3 times 11, 44 equals 2 times 2 times 11, and 54 equals 2 times 3 times 3 times 3. So the fundamental theorem of arithmetic is telling us that any natural number greater than 1, so in these four examples, my natural numbers are 4, 33, 44, and 54. And remember, they have to be greater than 1 for this to apply. They can be written as the product of only prime numbers. So in this example with 4, it's written as 2 times 2. And 2 is a prime number, so 4 can be written as the product of only prime numbers. 33 can be written as 3 times 11. And since 3 and 11 are both only prime numbers, 33 can be written as the product of other prime numbers. And then the same applies to 44 and 54, where all of these numbers here, when multiplied, equal 44 and 54 respectively, and they're only prime numbers. So that's what the fundamental theorem of arithmetic states, and this applies to any natural number that's greater than 1. So the next thing we need to talk about is prime factorization. Prime factorization is defined as writing a composite number as the product of only prime numbers using the fundamental theorem of arithmetic. So remember, the fundamental theorem of arithmetic tells us that any natural number greater than 1 can be broken down into a product of only prime numbers. Prime factorization is just actually doing that. Now, I don't think I have to explain any more about what prime factorization is. I already gave you some examples when I was talking about the fundamental theorem of arithmetic. For example, the prime factorization of 4 is 2 times 2, because the breakdown of 4 into only prime numbers is 2 times 2. So now I'm going to show you how to find the prime factorization of any number. So first you want to start with your number. So I'm going to be using 680 as an example. And so we're going to use something called a tree diagram. So you want to write your number near the top of a section of your page. You don't want to write it at the bottom because otherwise you're not going to have room to do this. So I'm going to write 680 at the top here. And what you want to do is you want to find any two factors of that number that multiply by each other to get that number. So two factors of 680, for example, are 2 and 5. It's divisible by both 2 and 5, so 2 and 5 are factors. But since 2 and 5 don't multiply by each other and get 680, they multiply by each other to get 10, I can't use those two factors for these purposes. So I have to think of two specific factors of 680 that multiply by each other to get to 680. Well, I know I can break it down into 68 and 10. So that's what I'll break it down into first. Because 68 times 10 equals 680. So you want to create two different branches off your original number and just break it down into those two numbers. And essentially, the way you find the prime factorization with this is you keep breaking down every number that's remaining until you're only left with prime numbers. So let's do that and see what it looks like. So first I'm going to break down 68 into 2 and 34, because 2 times 34 equals 68. And I'll break 10 down into 5 and 2. This 5 times 2 equals 10. So next, if I were to break down 2, well, I actually can't break down 2 because it's a prime number, and prime numbers can't be broken down any further. So I'm going to leave it and move on to the next number. So next here I have 34. So 34 I can break down into 2 times 17, because 2 times 17 equals 34. So next I'll move on to the next number, which is 5. And I can't break that down any further because it's a prime number. And then the next number is 2. And I also can't break that down any further because it's a prime number. So I move on to my next row of numbers that I broke down. So now I have 2 and 17 here. Well, 2 is a prime number, so I can't break that down any further. And 17 is also a prime number, so I can't break that down any further. So now at the bottom of my tree, I'm left with only prime numbers. And so what you do here is you count up how many of each number there is, or how much of each prime number there is at the bottom of the tree, and then use those numbers to create the prime factorization. So the prime factorization of 680 is 2 times 2 times 17 times 5 times 2. Because you look at the bottom of your tree and figure out what prime numbers are there. So I have a 2 here, a 2 here, and a 2 here, so that's 3 2s. I have 1 17 and I have 1 5. So if I look at my prime factorization, I have 2 times 2, so that's 2 2s so far. Here's my 17, here's my 5, and then here's my third 2. And then if you rewrite that in exponential notation, that would give you 2 to the power of 3, because this 2 times itself 3 times 5 times 17. And most of the time we are going to write prime factorization in exponential notation. So just to review, the way you find prime factorization is you write your number at the top and break it down into 2 factors that multiply by each other to get your number, and then keep breaking that down until you're only left with prime numbers at the bottom, and then you count up those prime numbers and put them in a prime factorization. So a lot of questions will test your knowledge about specific factors of a number. So now I'm going to show you how to find all of the factors of a certain number rather than just its prime factors. Now the reason prime factorization is so important is because to be able to find all of the factors of a number, first you have to find the prime factorization of a number. So I'm going to be using 200 as my example, and my first step is to find the prime factorization of 200. So the prime factorization of 200 is 2 to the power of 3 times 5 to the power of 2. And again, you would do this using the tree diagram, but I'm going to skip all the extra steps in finding it and just move on from here and show you what to do. So in order to find all the factors, you want to create a table, because in this table, you're going to be listing out your different factors. Because on the outside of the table, you're going to have numbers that you're going to multiply. So the way you use the prime factorization is you use it to fill out the outside of the table. So your next step is to list out each degree of each prime factor, including 1, on the outside of the table. Now this is where it gets a little bit tricky, and if you don't know what a degree is, it's basically just different powers of a number. So if it says each degree of each prime factor, well, one of my prime factors is 2, then different degrees of 2 would be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on, to the 4, to the 5, to the 6. And you get what I mean. So those are different degrees of a number, and specifically different degrees of 2, which is one of my prime factors. So my job is to list out all the different degrees of each of my prime factors in the table, all the way up to the highest one that shows up in the prime factorization. So I'm going to start with 2 to the power of 0 in this part of the outside of the table. Then I'll move on to 2 to the power of 1, then 2 to the power of 2, and then 2 to the power of 3. And then the reason I stop at 2 to the power of 3 is because 2 to the power of 3 is the highest degree that shows up in my prime factorization. Now you may be wondering why here I have 1, 2, 4, and then 8 when I need to list out 2 to the power of 0, to the 1, to the 2, and to the 3. Well, first, anything to the power of 0 always equals 1. So 2 to the power of 0 is just going to leave me with 1, which is why I start with 1 in any case. Next, I have 2 to the power of 1, and I just simplify that to 2 because any number to the power of 1 is equal to itself. Next, I have 2 to the power of 2, which I simplify to 4, and then 2 to the power of 3, which I simplify to 8. Now, if I move down into my column, I have to list out all the different degrees of my next prime factor, which is 5. So I start with 5 to the power of 0, then do 5 to the power of 1, and then 5 to the power of 2. And so 5 to the power of 0 is just equal to 1, because again, any number to the power of 0 equals 1. Then 5 to the power of 1 equals 5, and 5 to the power of 2 equals 25. So now that I have that all sorted out, and I have all my degrees of each prime factor, up to their highest degree that shows up in the prime factorization listed on the outside of my table, now all I have to do is multiply each row in each column. And so when you're finished with that, it'll look something like this. So in here, I've multiplied each row on the outside by each column on the outside. So I started with 1 times 1, then 2 times 1, then I did 4 times 1, and I did 8 times 1. And then I moved on to my next row. So here I had 5, and I multiplied that by 1, which is 5. Then I did 2 times 5, which is 10, 4 times 5, which is 20, 8 times 5, which is 40, and then 1 times 25, because that's my next row, which is 25, 2 times 25, which is 50, 4 times 25, which is 100, and 8 times 25, which is 200. And each number inside this table will be a factor. So if I look at this table, then my factors of 200 are going to be all the numbers inside. So 1, 2, 4, 8, 5, 10, 20, 40, 25, 50, 100, and 200 are the 12 different factors of 200. So now we'll do a practice question about finding all the factors of a number. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll go ahead and explain the answer. So the factors of 40 were 1, 2, 4, 5, 8, 10, 20, and 40. So as always, my first step in finding all the factors of a number is to find the prime factorization of that number. So I'm going to start by making a tree diagram and writing 40 at the top of my tree diagram. So now I need to find my prime factorization of 40. So I need to pick any two factors of 40 that when multiplied by each other get me 240. So I know 40 can be broken down into 20 and 2 because 2 times 20 equals 40. So that's what I'll break it down into first. So here I'll write 20. Oops, that's 200. And then here I'll write 2. So now I need to break down those numbers. So we'll start by breaking down 20. So 20 can be broken down into 5 and 4, I know. So I'll break down 20 into 5 and 4 because 5 times 4 equals 20. So I'll write 5 here, and I'll write 4 here. And now if I go on to my next number, 2, I can't break that down any further because it's a prime number. So I just need to move on. So now I'm left with breaking down 5 and 4. Well, 5 is a prime number, so I can't break that down any further. So I just need to break down 4. So 4 can be broken down into 2 times 2. And I'll write that here, 2 and 2. Because 2 times 2 equals 4. And now if I need to break down my next numbers, which are both 2s, I realize that I can't break them down any further because they're both prime numbers. So now I'm left with only prime numbers at the bottom of my tree, which means I can just count these prime numbers and figure out my prime factorization. So here I have 1, 2, 2, 2, and then 3 2s. And then I also have 1, 5. And those are my prime numbers at the bottom of the tree. And I didn't miss any of them. So my prime factorization, therefore, is 2 times 2 times 2, because I have 3 2s, and then times 5. And then if I write that in exponential notation, I can simplify this bit here, because 2 times 2 times 2, in exponential notation is just 2 to the power of 3, since it's multiplied by itself 3 times. And then that times 5. So now I have my prime factorization of 40. So now I need to use this prime factorization in order to create the table and then find all the rest of the factors. So if you'll remember, my first step is to create my table, and then on the outside of the table, list out all the different degrees of each prime factor. So first I'll create my table. So here's my top row, and then here's my column. So first I need to figure out what my first prime factor is, and that's 2. So in the top, I need to list out all my different degrees of 2. So I start with 2 to the power of 0, then 2 to the power of 1 in my next column, then 2 to the power of 2, and then 2 to the power of 3. And I stop here because 2 to the power of 3 is the highest degree I have in my prime factorization. So now when I simplify these numbers, 2 to the power of 0 is simplified to 1, 2 to the power of 1 is simplified to 2, 2 to the power of 2 is simplified to 4, and then 2 to the power of 3 is simplified to 8. And now in my column, I need to list out all the different degrees of my next prime factor, which is 5. So I start with 5 to the power of 0, then I do 5 to the power of 1. And I stop here because I have only 5 to the power of 1 in my prime factorization. Now, if you look at my prime factorization, you see it doesn't actually have an exponent. But remember, any number to the power of 1 is just itself, which means 5 is also equal to 5 to the power of 1, which is why in my table I stop at 5 to the power of 1. So if I simplify this, this simplifies to 1, because any number to the power of 0 is 1, and then this just simplifies to 5. So now I'm ready to multiply all of my numbers. So I just go row by row and column by column and multiply all my numbers inside the table. So first, 1 times 1 is 1, 2 times 1 is 2, 4 times 1 is 4, and then 8 times 1 is 8. And then next I have 1 times 5, which is 5, 2 times 5, which is 10, 4 times 5, which is 20, and 8 times 5, which is 40. And these are all my factors of 40. And so if I put them in numerical order, I get 1, 2, 4, then 5, and then 8, 10, 20, and 40. Okay, so the next thing we need to talk about is greatest common factor, which is also called GCF. So the greatest common factor is a relationship that can be drawn between two numbers. And so here's what the relationship is. The GCF of two numbers, so A and B, so if you have two numbers, it's the largest number that is a factor of both A and B. So that's why it's called greatest common factor, because greatest as in the largest number, common as in both have this number, and then factor as in it's a factor of both of them. So largest factor of both of these numbers. So let me give you an example. If I had the numbers 12 and 30, and I had to find the greatest common factor between 12 and 30, so I need to find the largest factor that both of these numbers have that they share, then it would be 6. And the reason being is because if I find all the factors of each of these numbers, so the factors of 12 are 1, 2, 3, 4, 6, and 12. And then the factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. Then the largest factor that they both have, which is why its common factor, is 6. Now they both share other factors like 1, 2, 3, and 3, but we're not interested in those numbers. We just want to find the largest one that they both have. However, the best way to find GCF rarely is to compute all the factors of two numbers. So now I'll be showing you two specific ways to find the GCF of two numbers. So as I said, there are two main methods for finding the greatest common factor. So I'll be showing you these two methods now. So the first method is to find the minimum common prime factors of each number and then multiply that by each other. So I find the best way to explain this is through examples. So I'll be doing an example here. My question says, find the GCF of 48 and 84. Well, if you're talking about prime factors, then you should assume that the first step is to find the prime factorization of each number. And in fact, that is the first step when you're using this method to find GCF. But I'm not going to go through the process of finding the prime factorization of each number because I can do that some other time, and we already learned about that. So I'll just tell you the prime factorization of both of these numbers. So first, the prime factorization of 48 is 2 times 2 times 2 times 2 times 3. And you'll see why I'm not writing this in exponential notation in a sec. And then the prime factorization of 84 is 2 times 2 times 3 times 7. So now I have all my prime factors and how many of them each listed out for each of the numbers. I have the prime factorization of both. If I look at what this says, it says find the minimum common prime factors of each number, multiply. So we have to remember that we're talking about GCF here, which is greatest common factor. And the word common means that they both share these numbers. So the greatest common factor will be a number that's a factor of both of these larger numbers. So if I'm looking at my prime factorization, that means I can also eliminate any numbers that these two numbers don't share as factors. So here I see in 48, I have 2 times 2 times 2 times 2 times 3. And in 84, I have 2 times 2 times 3 times 7. Well, they both have 2's in them. They both have 3's in them. But 84 has a 7 and 48 doesn't. And since I'm talking about the word common, which means that they share factors, that means I don't have to worry about the 7. I don't include it in my calculations. In fact, I can just cross it off and pretend it wasn't part of the prime factorization in the first place. And that's what your first step should be after you find the prime factorization. Get rid of any prime factors that they don't both have. So they both had 2's, they both had 3's, but they didn't both have 7's. So I got rid of my 7 here. So now your next step is to find the minimum common prime factors of each number. So I look at my 48 and 84 prime factorization, and I see that they both have 2's. 48 has 4 2's, and 84 has 2 2's. So it says find the minimum prime factors of each number, right? So the minimum amount that they both share is 2, right? Because 84 has 2 2's in it, and 48 has 4 2's in it. But they both have at least 2. So this is where it gets a little bit tricky because it's a hard concept to understand. Since 84 only has 2 2's in it, that's what I call my restraining term. I can only put 2 2's in my greatest common factor calculations. And since it says multiplied, I multiply them by each other. And so if you find a number that has, or if you have the prime factorizations and they have the same prime factors, you're going to use whichever one has less of each prime factor. So 84 had less 2's in it and only had 2 2's total. So I only use 2 2's in my greatest common factor calculations. Next, I move on to my next prime factor, which they share, which is 3. And I notice that they both have 1 3 in them. Well, they share this 3, which means I only have to put 3 in once in my greatest common factor calculations. Now, if one of them had 3 3's in it, which would be 3 times 3 times 3, and the other had 2 3's in it, 3 times 3, then I would only put 2 3's total in my prime factorization or my greatest common factor calculations, because they only share 2 3's. So that's this is where the word common also applies, not in which factors they have, but how many of each factor they have as well. So they only have in common 2 2's in this example and 1 3 in this example as well. So therefore, my greatest common factor are what I just derived, which is 2 times 2 and then 3, all multiplied by each other, and that would leave me with 12. Now, my second method for finding prime factorization, and this tends to work a little bit better when the numbers you have are a little bit bigger, is to reduce the GCF of the numbers, where the greatest common factor of two numbers, A and B, will be equal to the greatest common factor of A minus KB and B, where K is any number. So that was probably really confusing, so bear with me, I promise I'll explain it. So here I have an example that says GCF of 2008 and 2006. So here if I look at my definition, it says reduce the GCF numbers, which means I want to reduce these to smaller numbers, because I know finding the prime factorization of two large numbers, 2008 and 2006, would be a real pain, right? So if I could reduce it to smaller numbers and I'd still get the same greatest common factor, that would be really, really nice. So this is a method for doing exactly that. So it says where the GCF of two numbers, A and B, so in this example, then my two numbers are 2008 and 2006. And generally, you want to put your larger number as A. So 2008 would be my A, and 2006 would be B. And this means find the greatest common factor of 2008 and 2006. That will be equal to the greatest common factor of A minus KB and B, where K is any number. So the greatest common factor of 2008 and 2006 will be equal to the greatest common factor of A minus KB, which we're going to skip over for a sec. We'll just write it as A minus KB and B. And we know B is 2006. So I can leave 2006 in there. So this is where it's tricky, because this is where you could get confused and not know which number to put here. We know that the greatest common factor of 2008 and 2006 is equal to the greatest common factor of whatever this simplifies to in 2006 as well. So it says A minus KB, where K is any number. Well, if K can be any number, then I could say K is 1, I could say K is 10, I could say K is 1,500, or whatever amount that I wanted. But for this example, I'm just going to keep K as 1, which would simplify to A times, or A minus 1 times B. And if I simplify this GCF of A minus 1 times B, then that would simplify to 2008 minus 1 times 2006, because 2008 is A and 2006 is B. So if I were to simplify this, I'd be left with GCF of 2008 and 2006 will be equal to the GCF of 2008 minus 1 times 2006, and this entire thing simplifies to 2 and 2006. And so that's how I use A minus KB. It's essentially your first number, which in this case is 2008, minus some amount times your second number. So K is any natural number, so I used 1 or any whole number, so I used 1 in this example. And then your GCF of 2008 and 2006 will be equal to your GCF of whatever that result is, which is 2 and 2006. And now if I were given this problem, it'd be a lot easier, because the only factors that 2 have are 2 and 1, which means that the GCF of these two numbers, 2 and 2006, has to either be 2 and 1. So now we just have to figure out whether 2006 is divisible by 2, and it is. So the greatest common factor of 2 and 2006 is 2, which means that the greatest common factor of 2008 and 2006 is also 2. And that's how I use this to simplify. And since this one's a little bit more confusing, I'm going to do one more example where I have 1,400 and 135. And this is where you definitely want to use this method more, because with the 2008 and 2006 example, you might be able to figure it out in your head. But for this example, it's a little bit harder. So I'll use this method and I'll write GCF of A and B, which is 1,400 and 135, is going to be equal to the GCF of A minus KB, GCF of A, which is 1,400, minus K times B, which is 35, and B. Sorry, K is 135, and then B, which is 135. There we go. Okay, so now I have this written out in this format where the GCF of 1,400 and 135 is equal to the GCF of 1,400 minus K times 135 and 135. So now if I really want to have an impact on these GCF calculations, I want to figure out a value for K. So when I subtract that mass, like this section, from 1,400, it leaves me with a small number. If I write this out again, it'll tell you what the number is that I'm thinking of. It's 10. And I put 10 in for K, because remember, K can be literally any natural number, and it'll still work. Then I get 1,400 minus 10 times 135 and 135. So now if I simplify this, so I'll just write this section out again. Oops. 135 equals the GCF of, and if I simplify 1,400 minus 10 times 135, and 10 times 35 is 1,350, then that leaves me with 50, and then also 135. So now I'm left with a much easier pair of numbers to find the greatest common factor of, 50 and 135. So now if I wanted, I could use the first method where I find the prime factorization of each number, but I'm going to use the second method again. We're going to say the GCF of 135, and I'm going to use 135 as A now because it's my bigger number, and 50 will be equal to my GCF of 135 minus K, which I'm going to make 2 in this case, so 2 times 50 and 50, because I also have to include B there. If I simplify that again, equals 100, oops, so it becomes the GCF 135 and 50, that would be equal to the GCF of, and then if I subtract 2 times 50, which is 100 from 135, that leaves me with 35 and 50. And so now if you were to try and find the GCF of these two numbers, you could probably do it in your head. It would be a lot easier than if you tried to do it from 1,400 and 135. And then I could just do this in my head and say the GCF of these two numbers is 5, because they're both divisible by 5, but there's no larger number that they're both divisible by. So the greatest common factor of 35 and 50 is just 5, which means that the greatest common factor of 135 and 50 is also 5. And since we got that from 1,400 and 135, then the greatest common factor of 1,400 and 135 is just 5. And then to wrap up this lesson, we'll do one review question where I'll ask you to find the GCF of 756. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain the answer. So the correct answer to this question was 28. Now for this question, I'm going to use the first method, just because 56 isn't a particularly nice number if we were to multiply it by something and subtract it from 700. So I'm going to use the first method where I find the prime factorization of both these numbers, and then find whatever the most amount of each common prime factor they have is and multiply that by each other. So we'll start with the prime factorization of 700. So 700 can be broken down first into 107, which is probably the two easiest numbers to break it down into. Since it ends in 2 zeros, it's divisible by 100. So next, I can't break down 7 anymore because it's a prime number. So I'll break 100 down into 25 and 4. So 25 here and 4 here. And I'm going through this a little bit quickly because we already talked about prime factorization. So I break 25 down into 5 and 5. I'll break 4 down into 2 and 2. So 2 here and 2 here. So now my prime factorization of 700 is simply just 2 times 2 times 5 times 5 times 7. Remember, it's a little bit easier to write it out not in exponential notation when you use this method. We'll just do 700 equals that, and then I'll move on to my next number. All right, so I need to also find the prime factorization of 56. So 56, and 56 I'll write at the top, and I know two numbers that go into 56 are 8 and 7. And those are just numbers from your times tables. 8 times 7 equals 56. So now 7 is a prime number, so I can't break that down any further, but I can break down 8 a little bit further into 2 and 4. So 8 breaks down to 2 and 4. Can't break down that 2 because it's a prime number. And then 4 breaks down into just 2 and 2. So 2 here and 2 here. So my prime factorization of 56 would be, since I have 3 2's, it's 2 times 2 times 2 times 7, because I also have a 7. So now remember that my next step is to figure out what prime factors they do not have in common and eliminate those. So we're talking about greatest common factor, so therefore we need to eliminate the numbers that they don't have in common. Well, they both have 2's, they both have 7's, but 700 has 2 5's and 56 doesn't have any 5's. So now we need to eliminate all the 5's and just pretend like they didn't exist in the first place, because we don't have to worry about them at all. They're not going to affect our calculations. So I crossed off the 5's, and now I'm left with 2's and 7's. So now I just need to figure out how many of each number they also have in common, or the maximum amount that they both have. So 700 has 2 2's in it, and 56 has 3 2's in it. So I use the smaller amount, which is 2 2's, and I put that in my greatest common factor calculations. So 2 times 2. And then they both have 1 7 in it. So I also put that in my greatest common factor calculations because they have 1 7 in common. And then remember, I multiply all of those by each other to get 2 times 2 times 7. So when I multiply 2, 2, and 7, that leaves me with 4 times 7. And then that all simplifies to 28. All right, now to quickly review what we learned this lesson, we started with the fundamental theorem of arithmetic, which tells us that any natural number greater than 1 can be written as the product of only prime numbers. And then we had a few examples here where we broke down 4, 33, 44, and 54, which are natural numbers greater than 1, into the product of only prime numbers. Next, we talked about prime factorization, which is basically when we apply the fundamental theorem of arithmetic and actually break these numbers down into the product of prime numbers. And we learned about how to find the prime factorization by using something called a tree diagram, in where we write our number at the top that we need to find a prime factorization of. and then break that down into smaller and smaller and smaller numbers until we're only left with prime factors at the bottom. And then we count up those prime factors and multiply them by each other to get our prime factorization. And then we also learned that most of the time we write it in exponential notation. Next, we learned about finding specific factors of a number. And we learned that we actually have to find the prime factorization of a number in order to do this. So I used 200 as an example. We found the prime factorization. And the way you do this is you make a table, you list out all the degrees of each prime factor, which is all the different exponents they're raised to on the different rows and columns in your table, and then just multiply that by each other to get all your factors of the number. So all these numbers inside this table are factors of 200. Then we did a review question where we found all the factors of 40 and got 1, 2, 4, 5, 8, 10, 20, and 40. And then finally, we talked about greatest common factor, which is a relationship that can be drawn between two numbers, where it's basically the largest number that's a factor of both of the numbers you're trying to use. So we looked at an example where 12 and 30's greatest common factor is 6, because if we list out all the factors of these two numbers, the biggest factor that they have in common is 6. And then the best way to find GCF, we also learned though, is not to list out all the factors of each number and then just figure out which is the biggest, but actually there are two different methods to do it. So the first method was just to find the prime factorization of each number and then figure out which numbers they had in common in that prime factorization, and then figure out what the maximum amount that they shared was of each number and multiply that by each other. And then the second method was to reduce the GCF of the two numbers, so you can use it and find the GCF of two smaller numbers by figuring out that the GCF of two numbers, A and B, will always be equal to the GCF of A minus K times B, where K can be literally any natural number and 1 and B. So in this example, we did the GCF of 2008 and 2006 equals the GCF of 2008 minus 2006, where K was 1, and 2006. And then we just figured out that it was 2 and 2006, and the greatest common factor of those were 2. And then finally, we did a review question where we found the greatest common factor of 756. We used the first method where we found the prime factorization of these two numbers to figure out that the greatest common factor was 28. So that's all I have for this lesson. I'm sorry it's probably a long one, but there's a lot to get through for number theory meet 1, and the concepts are a little bit difficult. I did my best to explain it, and I really hoped it helped. See you next time.